Hi everyone. Today is the last lecture of the algorithms part of this module. Today we'll be talking about dynamic programming. This is a very interesting and quick and efficient technique to solve specific kinds of problems, and I'm sure that you will enjoy it because it's very clever in a sense. But yeah, so we will go through an example that we did last time, but from a slightly different point of view. After that, we'll have a brief, a couple of definitions and explanations of what that is, and after that, we'll do 4 examples, I think, and after that, it's just the homework. All right, so we have to revisit the Fibonacci numbers from last time. So if you remember, we calculated the nth Fibonacci number last time with recursion, and this is not the most efficient way. If you do it with a for loop, it will be a lot faster, and the reason for that is that if you have to calculate, if you have to calculate f of n, the nth, you have to calculate. I should have started to the right. Let me do that once again. So f of n. Okay, to do that we have to calculate f of n minus 1, and then f of n minus 2. Then to do f of n minus 1, we have to do f of n minus 2, f of n minus 3, and so on. But we see that this calculation and this one and everything that follows from f of n minus 2 is repeated, right? So we will do unnecessary stack calls. Okay, and last time I don't remember if we discussed or whether I told you what the complexity is of this way with recursion. It's phi to the n, where phi is the golden ratio. So you can assume that it's 2 to the n, and it's like exponential, which is really slow. And we know of a better way to do this, right? We can do it with a for loop, or we can do something clever that I'll show you in a second, which is gonna improve the efficiency and the speed of the algorithm. So first, is there a solution to that thing that we just did? So if you have the f here, the f here, and we know that everything that we do from this point on is going to be repeated here. We can just scratch that and say, well, we've already calculated this. Is there a way to kind of tell the program not to go into this calculation again? So any ideas on how to do that? So we've already calculated f of n minus 2, and here we would have to do it once again, or one of the values. So does anyone have an idea on how to do that? No? Okay, the idea here is that as soon as we calculate a value, like let's say that at some point we've calculated f of 3, we can store it in some array or something, and once we do that in another time where let's say on the right branch, if someone asks for f of 3, we don't have to go again and calculate it, but rather just say, well, we've already had this, right? We've already done it, so let's just return the value that we know. Okay, we don't have to go through all the way to f of 1 in order to know f of 3 once we've already done this calculation. So this technique is called memoization. I have a typo, memoization. And yeah, so I would like to show you how it's done. So we'll do the same algorithm as last time, but we'll do this array, which is just going to store the values for us. And then we'll see what does that thing have to do with dynamic programming at all. All right, so this is Visual Studio, so let's make a new project, which is going to be called Dynamic Programming. No, I have to, okay, so blank solution. And this one is going to be called Dynamic Programming. Okay, and the first problem that we'll solve is going to be Fibonacci numbers. Okay, why do I start with the same thing? Because it's a lot easier to explain how we go from recursion to recursion plus memoization and all the way to dynamic programming. So the idea is to start from something that you know and is familiar, and then go on to the more complicated stuff. So this is Fibonacci. Okay, so let's do the same method that we did last time. So it would be private static int Fibonacci of n, and in here we would what is it that we had to do? So if first, let's do the bottom of the recursion. So if n is 0 or n equals to 1, we would like to return 1, because the first two, let's say that the first two numbers f of 0 and f of 1 are ones, then we can just say return 1. And then our you know, if we had to store all of the values in an array, then it would be something like this. So 1 1 2 3 5 8 and so on, and this will be index 0, index 1, index 2, 3, 4 and 5. Okay. Right, then what we did was return Fibonacci of n minus 1 plus Fibonacci of I cannot call it the same with the same name as the class, so Fibonacci calc. Fibonacci calc of n minus 1, Fibonacci calc of n minus 2. Okay, and we saw last time that this was working fine. So console right line Fibonacci calc of let's say 5. So in if you start from f0 1, I'll just do that once again. So 1 1 2 3 5 8, and let's say that this is, you know, index 0 1 2 3 4 and 5. The fifth one would be 8. So let's do that thing. Let's run it. It takes a bit on the first go, so okay, we got that 8. Okay, if we do 4, it's gonna be 4. I'm sorry, it's gonna be 5, and yeah, so it works. It's fine, but it's really slow. Okay, and we can do the memoization technique, which just says, well, let's have an array that's gonna store the values that we've already calculated. So it's going to look something like this. Let's have static int memo equals new int, let's say of 10 elements. Let's say that we will not give more than 10 elements, but it doesn't really matter. I can give here 20, 30, depending on how many Fibonacci numbers I need. So let's say that it's 10. And what is it that we have to do? So as soon as we've calculated a value, we wouldn't like to calculate it once again. So in here, or maybe down here, we can say if memo of n is not 0, because this array here is initialized with only zeros, right? So if this array here already has a value inside, which is you know, one of the calculations that we made, then we don't want to go further and go into this line, which is the recursion. We would just like to say return memo of n. Okay, so maybe this thing actually has to be first, so we don't have to check for the bottom here, unless you know, so if we already have the value, then we should just give it back straight away so that we don't have any more computations going. Okay, and then what is it that we have to do otherwise? Okay, so otherwise we would like to save it in the specific place. So we would like to say memo of n equals Fibonacci calc of n minus 1 plus Fibonacci of n minus 2, and then we would like to say just return memo of n. This thing has to be Fibonacci calc. Okay, is that clear? We have an array, and as soon as we've calculated something, we store it in this array. In this case, once we get to n0 and n1, we would store in memo of 0 will be 1 and memo of 1 will be 1 as well. But after that, if we need to go through these values once again, then we will just reuse them. So how is the tree gonna go? So let's say that we have f of n, and down here we have n minus 1, n minus 2, and so on. So how do you think is that gonna go? Here we have n minus 1, n minus 2, and so on. Shouldn't we put a statement if the memo of n is different from null? Well, in this case it's not null. In C#, values are initialized with 0, and this is what I'm checking here. So if it's different from 0, meaning that if we have given a value there. So yeah, you were thinking a bit about JavaScript, I think. So yeah. All right. But yeah, anyway, so what do you think is going to happen? So this is n minus 2 and this is n minus 3, I'm sorry. So what do you think is going to happen with this technique specifically? We will go, okay, so do we save anything? Do we do anything at all that's going to help us? So normally, as we said, we would have to check all of the cases on this tree, which are quite a lot. But is there anything that we save? Is there anything that I can just scratch and delete and not calculate ever again? The second branch, is it just that or is it more? Sorry? Every second branch. Or we are going to be left with just this line, which is going to go n minus 3, n minus 4, and so on up until we get to 0 and then 1. So in here we just go through this calculation just once. We store every single value in here. So we'll have f of 0, f of 1, f of 2 up to f of n, and every time when we call it again somewhere, it doesn't matter where, then we'll just give the value back because we already have it. So this is of complexity O of n. Yes. So this is linear. This is very, very fast. The only thing that's probably faster of the more common ones is O of log n. But this one is still really, really fast. You have to try really, really hard to make the computer hang or something. But in the other case, it was phi to the n. So phi is around 1.6, I think. Which is, so once you try to calculate something like 20 Fibonacci numbers or something, it's gonna hang, or I don't know, 30, 100 or something. Whereas here, it would just do everything that you want, like up to, I don't know, a couple of billion, maybe, I don't know. All right, so this is the way, and this is sort of what you do in dynamic programming if you think about it. So let me go on to the next slide. Any questions here? No, everything is fine. Okay. So dynamic programming is a method for solving a complex problem by breaking it down into a collection of similar sub-problems. So this is something that we haven't seen so far, but if you follow, like an algorithm of steps, if you want to think about it, where you start with a problem that is done with recursion, and then you come up with some clever memoization method. In this case, it was like really easy, but it may not be. Then you can convert it into dynamic programming solution, which is a bit different. Okay, so you solve each of the sub-problems just once and then store their solutions for later use. Okay, the act of storing is called, as we said, memoization. I'm sure that I wrote those correctly, but I guess there is auto correct inside here, so yeah. Dynamic programming can be roughly described as recursion plus memoization, but we will do it another way, which is the bottom-up approach. So if I have to do, if I have to explain what that is with the Fibonacci case, this is, you know, we had to do f of n. I'm not going to draw that once again. So here we have some tree branches and so on. Here we have some more as well. The bottom up means that you start from the bottom of this tree. So every recursion is going to have a tree like this. Okay. If you remember last time, say the problem with n factorial, we had just a single branch because we were calling the recursion, you know, just once, and we had to calculate only the previous number. For the labyrinth, we had a starting point, then we had 4 directions, so our tree is going to get even bigger, and you know, each one of these will have even more, and so on. So we start always from the top. So once you do a recursion, you say, well, I want to find what f of n is, right? And then you start going going down along this tree, you know, along the stack calls, if you want to. Until we find a solution that we have. In this case, this is somewhere down here. It will be f of 0. Okay, and the way we are going to be doing it now. So once we've done something with memoization and, you know, keeping track of each step that we've calculated already, we would like to do it the other way. So instead of going from top to bottom, we would like to go from the bottom the other way. And this is the algorithm that you already know. So how would you calculate a Fibonacci number, right? You would start from the bottom. You would start from I equals 0, and then you would add some elements, but you have to store the values that you've calculated, or at least the last two ones. So if you have 1, 1, 2, how would I calculate this 3, right? I would have to have the previous 2 ones, so I have to store them somehow, right? To get this 3. And this is how you do it with a for loop as well. So you go from I to 0, and you work your way up to f of n, right? And this is what that dynamic programming does. So we started with a problem that is defined recursively, which I told you last time is, you know, a hint that you should use recursion, but in some cases you can optimize that quite a lot. So the optimization from phi to the n up until, you know, O of n, that's quite big, right? Okay, so we will use, so in the next couple of examples, we are just gonna mention how would you solve this with recursion. I'm not gonna write any code on recursion or something. So we'll just say, you know, how would you do this with recursion, and how would you solve it with the bottom-up approach. Okay, so does any of you remember from school, if they've done it, what is an induction in mathematics? Anyone, like, if anyone had, or if anyone remembers, then induction? No? No. Okay, check. Just a second. Okay, so no one in here knows what that is, but if you do know, like if you're a mathematician or you remember that from school, dynamic programming, or the bottom-up way, is the same thing as induction, if that thing speaks to you. So if you know that very well, it's the same thing. For those of you that don't know what that is, so it's everyone in the room now, and for those of you who are watching online and they have no idea what this cute word is, then just ignore what I'm saying. Okay. There are several steps that you can follow to solve a problem like this, but normally you would have to have solved a lot of problems similar to the ones that I'll give you a bit later on. But normally it goes something like this. So first you have to split the problem into similar sub-problems. So like imagine f of n. Okay, so someone tells us to do the complicated thing to calculate f of n. And we would like to solve it in, a smaller sub-problem. So imagine, so to solve f of n, someone tells me that I have to know what f of n minus 1 is and what f of n minus 2 is. So this is already, already split into smaller sub-problems for us. Then you have to characterize an optimal substructure, which is something that for this specific example is not valid, but I'll show you in the next one what's that about. Then you have to recursively define the value of an optimal, which here is the same thing. So once we have f of n minus 1 and f of n minus 2, we can just go to here, basically, and calculate the next one. So this is like our step with the information that we have of the smaller sub-problem. How would you solve the bigger one, which is, say if I have f of 2 and f of 3, I would have to find f of 4, which is the bigger problem, by splitting it into smaller ones. Okay, then you have to compute the value bottom up. So starting from the bottom of the recursion, or starting from the base case, which in this case is, f of 0 is 1 and f of 1 is 1. Then you work your way up, and you will get your final answer this way, instead of just with recursion starting from the bigger one and working your way down, which is very ineffective. And then finally you have to construct the optimal solution, and that's only if it's needed. So if someone asks you how many steps are there to do something, then you can count those, right? But if someone asks you, well, what are all of the numbers from 1 to n, Fibonacci numbers, then you would do the algorithm differently. So let me show you how that is done. So let's say that I tell you calculate fn, but only use an array of let's say 2 variables, maybe 3, let's say 2. How would you do that? So with the for loop, with an array, that's very, very easy. You just store them all, right? But what happens if someone says, well, just give me f of n, okay? I don't care about what all of the numbers are. I just need f of n. How would you do that? I guess I'll have to pause here for the people to think a bit. Okay. Okay, so you just need like, I think 3 cells are enough. Maybe you can do it with a 2, although I'm not really sure. Let's say that we have, the 1, and the 2. Okay, and this is again in a for loop from 0 to whatever. But at each step, what is it that we do? So let's say that this 2 we haven't calculated yet. So we have 1 and 1 equals 2, right? And then we don't need that one anymore. Okay, so we bring those 2 back, and we say, well, in the next step we have 1 and 2. What is this value? Well, that is 3. And then we don't need this anymore. Calculate this one. Sorry, move this one, and we'll get 2 and 3. And then this is 5. We don't need this, and so on. So you can. So this would be the pure bottom-up approach, where you don't need the whole information that you can save, right? But if someone asks you now, well, what are all of them? Then you can construct them, but that's only if needed. You would just need more space. Normally, that all of this information is stored in some kind of a data structure, whether that's a list, a dictionary, to like a matrix or something. It doesn't matter. It really depends on the problem. Okay, so this is all, general talk, and I would like to go into the examples as soon as possible. You don't even need to know all of this, but with the 4 problems that we will solve, I hope that you will get the hang of it very, very quickly. So I would like to spend more on these. So these ones are without demos, like in code, but the more important thing is to understand how we do it. Okay, so we have a bunny, which is allowed to move only right and down. Okay, it's not like last time where we allowed every direction, just right and down. Okay, and we wanna see in how many ways can the bunny reach the carrot. Okay, and before we even start to think, I just like to mention that, remember just the previous slide, I tried to explain, do you have to construct the solution in this case? What do you think? So I said you in one case, if needed, you would have to construct the solution, and I'm asking whether this is the case right now with this question. No, it's not. They just ask us, in how many ways can this be done? But if someone asks you, what are the ways, so how many and what are they, then you would have to somehow do something extra in your algorithm to provide this specific information. All right, so let's try and solve this. I cannot zoom that much, so I guess that is fine. Okay, now let's think. I guess the first one, it will be kind of hard, but I hope that the second one will be easier. So the idea here is that assume that we are in some cell, right? Assume that we are here, going down, to the carrot. So the idea here is, imagine that we are here, and we've already solved everything before that. Okay, so splitting it into smaller problems. Let's assume that the carrot is not all the way down here. Let's assume first that it's here, then it's here, then it's here, then it's here. And now I'm saying, well, imagine that the carrot is here, and we've already solved for every single cell before that. So this one, this one, this one, and this one. Imagine that we've solved how many ways are there to get into each cell of these ones. Okay, so let's assume that these are some numbers. So this is like A, this is like B. Okay, we know what those are. Assume that you've solved it. It doesn't matter how, just assume that you did. So now that you have this information, okay, and this is like C and D, how would you solve, or how many ways are there to get into this cell? Imagine that the carrot is here. Anyone? I'm not asking for a number. It's just, we have to do something with like values, but it's definitely not 5. I think we'll see how much that is. I'm not going to spoil the question. Okay, I can go through CDB and through, okay, but that's, the answer. But assume that this is a general cell. Okay, it's not the one that I give you, it's just a general cell. Okay, I'm sure that you can calculate it here, but again, so imagine that in C is the number of ways that I can reach from this thing here, from the 0, 0 to C, to this cell. So this is the number of ways that I can go. Sorry? A plus B. Just A plus B. Okay, so the answer here is A plus B, right? So how many ways are there to get to B? Sorry, we already have it to B. It's B, right? How many ways are there to get to this cell? Well, it's A, okay? And how many ways are there to get into this cell? Well, I can only go from the top cell and from the left cell, right? Because I can only move right and down. Okay? Is that clear? This is the most important thing. in this problem. So in this cell, I can only come from the top or from the left cell, and I already have calculated how many ways are there to get here and here, and so I can just say, well, this is a plus b. Okay, and this is our I would say induction step, but then I would confuse you. This is the smaller sub problem that we have and we've solved, right? So we have, if I take a random cell, so let's say this one, what would the answer be? How many ways are there to get from here to here? It's just the top and the left cell, depending on what the number is there, but I know that I've already calculated it, right? So I can just do this. So if that's like x and y, this will be just x plus y, and this is true for every cell. Okay, we did the harder part now, and let's do the easier part, which is just now the calculation itself. Okay, so we have a sort of a formula or a way of thinking, but we still don't have a base case. So let's come up with some base cases that we can use to fill in the table. So how many ways are there to get into this cell? It's just one. How about this one, the right one? Just one. This one? Okay, so all the way to the right, there is only one way to get there. The same is true for the bottom, by the way. Alright, and now let's start calculating. So how many ways are there to get into this cell? Just one. I can only go from the top, so these ones are not allowed. So there is no way I can go from the left. So this is just one. How about this cell? 2. How about the next one? 3, because I can go two ways from the left cell, and I can go one way from the top cell, so that's 3 now. The same way that this is going to be 4. Okay, how about this one? This is 2, this is 5, this is 9, and here 9. Let's do the other one quicker. So this one 1, this one 2, 3, and then the rest here are just 3s because I cannot go from the top. Okay, so finally the caret 12, right? Because I can only go 3 ways from the left and 9 ways from the top. How would you solve this before the lecture that we had today? You would, okay, how about if, so the answer was I will take the pencil and, okay, so how about if you have a grid of 1000 by 1000 with at least, say, 50 of these? You would waste a lot of time. Okay, so last time we did a problem which was very, very similar. How would you do that? Recursion. Okay, so you would go through every single path, and see how many are there. So if you remember last time when we were solving the labyrinth question, we said that we can go in all 4 ways, right? And then we had all of the solutions listed, and we counted them to be 3, right? So we can do the same thing with recursion, right? But instead of saying, well, I can go top, left, bottom, and right, we just say, well, I can only go these 2 ways, and the problem is absolutely the same. Okay, I will get however many ways are there to do this, and I will get them listed. I can get them counted, and so on. But what's going to be the complexity of this algorithm if we do it recursively? Sorry? Exponential. Okay, some value k to the n. I think that's correct. Yeah, I think that is fine. I'm not sure whether that's 2 to the n or 4 to the n. I don't know. It's just some constant to the n. What do you think of the complexity of the algorithm that I just described? What's that gonna be? O of n is not correct, but it's it's still going to be better than k to the n. Okay, think about what the algorithm does. I go through every single cell of these ones, and I do some calculation which takes a constant amount of operations. So how much is that gonna be? Sorry? N squared. And that is the correct answer, given that this is n and this is n. So if you have n rows and columns, then that's n squared, because I have to visit each cell once. And how many cells are there? They're n squared. Or if they're not the same, I think in this example they aren't, that's going to be r times c, rows times columns. And that's that. So which one is better? Is it this one or this one? It's the n squared, and by quite a bit. All right. How do you like dynamic programming? It saves, it saves a lot of time, and it's very, very clever. And because it's clever, it's also kind of hard to identify it or how to solve it. But you can get used to it. So what is it that we did in this case? We started, and that's like the most important thing if you're trying to solve a problem this way. We assumed that we are at some place, and we've already calculated everything before that. Okay, and the answer is, how would I calculate this specific cell in this case? Okay, that is really, really key. You just assume that you have it. So I have the A and B here, which is the precise answer of how many ways are there to get into this cell and this cell. That's A and B. Is there a way to calculate the one that I'm looking for? And in most, like in the next example, it will be very, very similar, but in the two after that, it's not going to be that similar. So you have to identify, so this is the step from the previous one, you have to characterize or define the optimal substructure. So in this case, the optimal substructure is that we can identify for each cell, imagining that the caret is here, we can identify how many ways are there to reach this cell, which gives us the A, the B, and then the rest is easy. But identifying what you need, or what's the optimal substructure that you need, is probably the most complicated thing about this way of solving problems. But once you get used to it, the rest is very, very easy. So I know that I have this and this, and can I do this thing in the middle? Well, I can, so it's fine. And then we solved it, and it's very, very simple. It's a lot simpler than actually coming up with a recursive way of going around a labyrinth. Okay, so I'll show you the next one, and I'll have a break so that the people in here can think how to solve this problem. So the bunny is allowed to move right and down. It's the same thing. What is the largest number of Easter eggs the bunny can gather when reaching the caret? So we start here. We have to finish here, but we have to finish gathering the most Easter eggs, and the number of Easter eggs is given in a number in the top left corner of each cell. Okay. And now, the previous one was very easy to calculate straight away, by with a piece of paper and pen. This one would not be, So this is the point. This can be solved very, very similarly. So I'll just give you some time to think. Maybe you have to write it on a piece of paper. Maybe you pause the video at home and then try to do it yourselves. But yeah, let's have a short break, and we'll get back with the solution. Okay, so someone guessed the answer, but I'll just recap once again. So it's the same sort of thinking, and since the example is very, very similar, then we can just do the same thing. So let's say that we have here that we want to find this value, okay? The maximum number of Easter eggs that we have right here. And imagine that we already have the maximum number here. Let's say that that's B. Let's say that that's A. So we have A is the maximum number of eggs that we can get in this cell. B is the maximum number of cells that we can get in this cell. Okay, so how would you calculate the maximum number of cells here. Okay, so from this cell we can only come from the top cell and from the left cell, and in here we have 3. So what would be the maximum number that we can get at this cell? Well, that would be the maximum between A and B. Sorry, A and B. And then we have to add 3 to it. So if it's like, if up here, let's say B is 5 and at A is like 4, the maximum would be to come from the top, which is 5 plus 3. In this cell we would have to write 8. And that's that. Okay, so let's fill in the table once again. Again, the problem is very, very similar to the previous one, and that's why it's so easy to guess it. But with the next one, I have to give you a bit more time to think about it, because it wouldn't be that easy to get it on the first go. All right. So how much? What's the maximum number that we can get in the right cell? 2. The next one here. 3. The next one here. 4. This one here. 8. This one here. 11. All right. This one down here should be 5. And the first one that's more interesting is this one. This is going to be 8. So that's going to be 5 plus 3 instead of the 4. So it's better to go this way instead of this way. If we go in the first way, we will get more eggs. Okay, how about this one too? 10. It doesn't matter which way we go. Okay, and then we have this cell here, which is going to be 12. Okay, this one is going to be 9. This one is going to be 11. This one is going to be 14. This one is going to be 18. Okay, and then we have to calculate on the left as well, because we would like to know whether this 18 or the number that we'll get here is the same. Sorry, well, which one is bigger? All right, so this one is 2, this one is 6, this one is 10. The one below here, oh yeah, we can't do that now. So this one here is 9. Now what is this one? 12. This one is 12. This one here is 13. It doesn't matter which way we go. Then we have 15, 16, 17. So it was, very, very close. But in the end, here we have 18 when we take the caret. Okay, but this only gives you the answer, right? So there is no way, at least right now, there is no way to reconstruct what was the way that we went, or is there? So how did we get to 18? So first we came from here, then we came from here, then which was the way we went? Up, up, then left, and all the way to the left. Okay, so this is quite important. So if someone asks you, well, give me the cells that you went through to get to here, you would have to do something extra, which is an extra algorithm that you have to do in order to reconstruct the path that you went. And we did it verbally, so if you had to write this down, I'm sure that you wouldn't have problems. So in this case, it's kind of easy. How would you solve this if you didn't know about DP, dynamic programming? Recursion. Okay, you find all possible paths, calculate for each one of them, calculate the number of eggs that you've had, and then pick the maximum one. Okay, which is again gonna be an exponential algorithm, and in this case we did one with is the same complexity, which is R times C. Okay, is that clear? Everything so far? The thing is, these were very, very similar, but I just want to show you, knowing one specific problem like the first one. So let's say that you've seen this one and you know that it can be solved with dynamic programming. Then you can go on to another one which is sort of similar, add a bit of complexity to it, meaning that it's harder, not the complexity that we use to check how efficient algorithms are. So you go to a similar one and you solve that one as well. Okay, so the point here is that right now we just know only one problem of sorts, and the more you solve, like the more generic ones or common ones you solve, you'll be able to apply this knowledge into something which is you know, more complicated or, you know, different. So this is why we will take two more, which I'll write in code that you would have to extend in your homework. But yeah, those are, you know, now different. Okay, so I would really like to delete this image right now so that you can think clearly. Okay, so given a set, which in this case, you know, is just some set of numbers. Okay, so we have 3, -1, 7, -2, 0, -6, 1. Can we obtain a subset with sum 0? How about a sum of 10? How about a sum which is just a given number s? Okay, can we do that? And let's first discuss how would you do this with recursion. Okay, so the, you know, the obvious way, or I don't know if it's that obvious, but I think it is. Okay, so if you have to find a subset of this set, this can be done in a number of ways, and you have to go through all of them, so that normally implies recursion or some. So if someone tells you brute force, this means try all possible things, like all possible cases, and this normally implies recursion. So how would you do that? And I have mentioned this question like at least 3 or 4 times during this course, like the whole course. Okay, so try everything. Store the values in some kind of array. So let's say that I pick this one, and this one. Store them in some array with the sum and so on, and then check after that whether the sum is the one that we need. That is one way, but I have given you another way which is a bit more clever, but it will have the same complexity in the end. So okay, so let's first discuss what's the complexity of this algorithm specifically. How many subsets are there of an n set, a set with n elements? In this case we have 7 elements. So how many checks would we have to do? Someone said n to the power of 2. N to the power of, so n to the n. No, that's not that. Okay. No, it's not n to the power of n minus 1 as well. Okay, so let's solve this. So this, you know, this is a fun, like a nice thing to do. So let's start with, okay, so I'm asking you, what's the complexity of something like this with recursion? So we have to basically find the number of subsets of an n set. Okay, we're not gonna prove that, but let's just assume, or no, how would you check that? Let me pause just for a second here. Okay, sorry about that. Okay, so let's get back to the question. How would you find the number of subsets of a set? Like if you're not a mathematician, but you know, you just want to check, right? You just want to guess. No, it's not n factorial. Okay, so how would you approach a problem like this without guessing? That's my point. Combinatorics. All right, but then that would be kind of hard, I think, as well. So how would you approach that? It's sort of a, again, it's sort of a dynamic programming problem. What's the number of subsets of an n set? Try smaller values. Okay, if someone gives you a generic problem, the first thing that you want to do is, okay, so what happens for the case n equals to 1, n equals to 2, 3, 4, and so on. And then it might give you an idea that you can follow, right? So this is the essence, I think. So okay, so let's start with a set of one element. So let's say that this is D3. How many subsets are there? N. I'm just giving you a specific example. Okay, but for, to make things better, or just to make the formula at the end better, we would consider the empty set also a subset of the whole thing. So we have the 0 and the 3, so that gives us 2. Okay, how about if we have the 3 and the minus 1? Let's do that as well. Here n is 1. Let's do that thing as well. I think green is better, but yeah, okay. So how many subsets are there? We have the empty one. After that, what is it that we have? So okay, so the minus 1, the 3, and the 3 and minus 1, which is 4. This is for n equals 2. Okay, how about the next one? And I hope that you can guess what the answer is. So 3 minus 1 and 7. And I'm gonna type because that's annoying. Okay. Okay, first, what are the subsets? So the empty one, 3, minus 1, 7, 3 plus minus 1, 3 plus 7, minus 1 plus 7, and full set, like, right? 3 minus 1 and 7. So we have how many? 8. Okay, sorry, this is 8 is here, and n equals 3. So now can we guess? It's not n to the power of 2 because 3 squared is 9, and we have an 8. So it's going to be 2 to the power of n. Okay, so in the first case, 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8, and so on. That's the number of... Okay, so how many steps, or what's the complexity of the recursive algorithm, which is going to find, all subsets and then find all of the sum, is going to be what happened. It's going to be 2 to the power of n. Okay, and we want to come up with something that is smarter. So one way that I told you, I think, it's smarter, but it's not better. Okay, so without a recursion, you can generate all 0, 1 numbers with 7 digits. Okay, and if it's a 1, say that we have something like 1 0 1 0 0 0 1. Okay, so if we have a 1 in this number, then we take the 1, then we take the 7, I think. So this is going to be the 1, this is going to be the 7, this is going to be the 3. And we get a sum of 11. So this is just a cleverer way to generate all combinations. But again, we will just have to do 2 to the n things as well. I think I mentioned this last lecture. People were looking confused, kind of. Right, so if you have a set, an element is either in the subset or not. Okay, in how many ways, or how many subsets, or how would you do that? Well, just generate all the numbers I from 0 to 2 to the n, go to their binary representation. If you have a 1, you add the element to the subset, and then after that, if it's a 0, you don't. And this way you will start with 0, 0, 0. The last term will be just with ones, and you will have generated everything in between. But this is going to be again with 2 to the n complexity, and we would like to find a smarter, better way, which is going to have a complexity which is a lot better. So in here I would pause and I'll give time to everyone here to think about it. It's I wouldn't say it's more complicated, it's just a different type of question that you can approach the same way. So I'll pause and I'll get back in a second. Okay, after a lengthy discussion, we managed to reach a solution to this problem, which does not require a recursion. So let's break this down into a smaller problems, right, and try to identify what the step is. So let's start with the empty set. Okay, so what we would like to do is, find a way. How would you do this by hand, starting with the smallest sets. The first one is the empty set, which let's assume has a sum of 0. Okay, let's add the 3 in here, and this clearly is going to have only sums with 3. Okay, on the left we have just the subset, or trying to get to this set. On the right we have all of the possible sums that we have that we would like to get. So instead of starting with n, as given n, can you do a sum of n? We would like to calculate all possible sums, but in a efficient way, instead of just thinking about this n. And then finally we can just check, well, is it in this list of possible sums that we have? If yes, then we can get it. If no, then we cannot. All right, so we have 3. Then we have to add the -1. Okay, so what are the possible sums here? Sorry, here clearly we can do the 0 as well if you just don't add any elements. Okay, so we still have the 0, we still have the 3, we also have -1, and we have the 2 as well. Let's add another one. So 3 -1, 7. And let's do those. So on the top we still have 0, 3, -1, 2 as our possible sums, and then we have the 7. So I guess I should write down that 7. Then we have 7 -1 is going to be 6. 7 plus 3 is going to be 10, and 7 -1 plus 3 is going to be 9. Alright, but this right now it doesn't tell us much. But what happens, so now let's try to identify what's happening when we add a new number to this set. So clearly this thing repeats, and clearly we have some new values which only come from the 7 here. So let's do one more step, I guess. So 3 -1, 7, then we have -2, and I'll write that -2 in red so that we can see what's going on. So in here we have to repeat all of those, right? So they're still here, but then we have the -2 which is added. And if you think about dynamic programming, what does the previous information give us? Well, these are all possible sums that we can do with the numbers 3, -1, and 7. If we add the -2 and we add it to all of these possible sums, then we will get all possible sums with the -2 as well. So what we have to do is, -2, we have 3, which is 1, math is hard, -3, then we have 5, and so on. We just do all of those with the -2. So it's like we have a list, right, that we keep adding numbers to depending on which step we are in. So the first half of this list is going to be repeated from the previous step, right? And then we have to add two more values in we have to add the same number of values here, but add it with this -2 here, which is sort of all right. And we had a brief discussion on whether the recursion thing is better or this one is better. And the answer is that this one is definitely a lot better. So the recursion is 2 to the n, and I think this one is with complexity n squared. I think it may be something a little bit more, but it's definitely polynomial. Okay, and polynomial independently of what the power is here, even if it's n to the 5 to the 10 to the 1 million, it's still quicker than this thing. But it's definitely polynomial because we have to go through each value, add it once to the set, okay, and then we have a list that we always have to add values which are like new values to it, which are some number depending on n, but it's definitely not exponential. So I think that's n squared, but I'm not completely sure, but it's definitely polynomial time. We can express it with n to some power. Alright, and I deleted the picture, which I am gonna show you now. So this is similar to what we will be doing in the demo now. So this is a table which describes something similar to what I've given you. So we have a set. This one is different. It's a little bit smaller. But we have a set which is of 3, 1, 1, 2, 2, 1. Okay, we start with the empty one. We have a 3, we have a 3 and a 1, 3, 1, 1, 3, 1, 1, 2, and so on, up until we get the whole set. And then we have some array or some list or a dictionary, hint, hint, which is going to tell us, well, can we do this sum? Can we do the sum of 0? Can we do the sum of 1, of 2, of 3, of 4, of 5? Up to how much? Up to the maximum sum that we can get from this array, which we don't even really care about that much. We can calculate it at the beginning. So what is the maximum sum for this set? Oh, come on, it's 10, right? So 3, 1, 1, 2, 2, 1 is 10. So this table would normally go up until 6, 7, 8, 9, 10. And can we get every single value from here will be determined whether we can get a true value inside this cell. So can we get a 0? We have a true, so there is a way. Okay, for this one, is there a true? Well, yes, there is, so we can obtain it somehow. Okay, so let's start and do the same thing at least for a couple of values so that we can proceed to the algorithm. So the 0, clearly we can do it with the empty set. It's a bit of a problem, but you will have to solve it yourselves when the sum that we have to find is actually 0, because in this case there is no subset which gives a sum of 0, but that can be very easily fixed. Okay, so if you don't get it in the first in our list where we keep all of the possible sums, if it only appears in the 0th position, then that means that it cannot be done. But if it appears like in the 7th or 10th, it can be done. But let's just not worry about that. So okay, so let's take this set. Okay, can we have a 1? Well, clearly no. If we add the 1 though, then that's fine. So we can do that. That's true. Let's take the 2. So let's add a the empty set is false. This one is false. With the 3 and 1 we can't do it. With the 3, 1, 1 we can do it. So that is true. Let's go on to the next one. The 3 is clearly true. Can we get a 4? Yes, if we get a 3 and a 1 as a subset. But this all, true and false comes from the calculation that I just described. So at each step, if we have a new sum, we just say, well, this sum now has a value of true or false, depending on whether we can get it or not. For the 5, I guess we have to go all the way. Actually, it's not all the way. It's up to here. We'll have the 3, 1, and 1. But for something like 10, unless we go to the very end, then it will be false all the way unless we get all of the numbers in here. All right, so let's write this down, and then you would have to expand on something in your homework. So this is 2, and this is subset of some n. Okay, so this is, come on, subset some n. Yes. And we would like to have a method which is going to return a boolean, which is going to say, well, can we do this sum or not? So let's call this is there sum. We have to give an array, so something like new int, and in here we will give some values. I'll just have to copy the values from the presentation, so let me copy all of those. Okay, and then we have to give, what is it that we have to give? We have to give a sum that we have to find. Okay, and all of that I would like to put in a console write line. What is the problem? Sum does not exist in the current. Oh right, sorry. Yeah, this is just like what sum do you want to get. So we'll try with 7 or with something else. And I want to put this in console write line. Or okay, so yeah, let's put it here, and we'll do that later. Okay, and then we have to give the method, which is going to be private static bool is there sum int. We'll call those elements in sum. Okay, so I mentioned dictionary a little bit earlier, because for each sum that we find, for each new sum that we find, we would like to put it in some sort of a data structure, which is going to be something like this. So here are the possible sums that we can get, and here we just have to give true or false depending on whether we can get this value, right? So let's write this down. So var possible sums dictionary equals new dictionary, and what are going to be the values here? So what are going to be the keys? Int and bool. Okay, so how are they initialized? Does anyone know? It's empty at first, right? Yeah, 0 and false, but we don't have any elements right now, so we would like to push or to add only the ones that we found. Otherwise, the rest will not be found, right? Okay, so let's try with the 0 because we said that we assume that we can always get a 0 from the empty set. So let's say possible sums dict of 0 equals true. Okay, I can either do it this way. I think I've discussed it in the first lecture, or I can do possible sums dict dot add, and here I have to give 0 true, right? So there are two ways. This one looks very much like an array of booleans, and it's pretty much the same. But once we want to access all of the keys or some key, that will be a lot faster than going through all of them, I think. I'm not sure. Maybe. Okay. So, oh yeah, the problem is that an array cannot have an index -1, right? So if you have a sum which is like -1, whether it's true or false, if we store that in an array, we cannot have the index which is -1, and in a dictionary we can. So yeah, that's the reason why we use this structure right now. There is a question: why do we do that? Why do we do what? because we always, so the question is, why do we have this line of code? We always assume that we can get the empty set, which has a sum of 0. It's just the empty set. So the empty set has a sum of 0. Okay, if someone gives you a 0 here, then you would have to slightly change the algorithm, but that's going to be left for homework. Okay, but right now with the algorithm that I described, we always start with the empty set, which has a sum of 0, and then by adding the 3, we also like to have here is 0 and 3. Do you know why I do this 0? Because when I add the next element, I would like to have the same algorithm, which means, you know, take each of these values to obtain the new one. So by having the 0 here, I make sure that I have the -1 because I've added it with the 0. I don't have to make any extra checks, or, you know, just to add elements by hand. But I've sort of solved this part of your homework already, so yeah, I'm just gonna stop talking about that. Okay, so then we would like to have a list which is gonna hold all possible sums that we can get. So this is gonna be var all, or just possible sums, and this is the list that we add elements to. So you remember when I was saying, well, when we add a new element, we have to add all possible sums to it. And this is the set that will keep extending depending on how many values we've added. So var possible sums equals, I would just like to put it as a list. So new list of int. Okay, and of course we have to do possible sums dot add 0. So these are like the, so you remember that in recursions and the bottom up thing, you always have to have a base case, right? And in this algorithm, the base case is, you know, always add 0, or always add the first element, or, you know, there has to be some base case so that we can start from it. All right, then we have to make a for loop through all of the elements that we will add, you know, up until we get to our original set, which has the O elements, and we've calculated all values. So this is the step where we start with the empty set, and then we add the elements 3, then -1, then 7. This is basically every step that we have to take care of once we do once we calculate these elements. So this is elements dot length and for loop. Okay, so each of these possible sums at each step has some values which are fixed, and then we have to add the new values, right, which are going to be, you know, some new ones. And so to do that, I would like to store them in another array. So for possible sums to add, is it clear what this array does that I'm going to do now? It's a new list of int. So at each step we have to add new values to our possible sums, and we are just going to add them in a separate array, because otherwise I would not be able to write the next line of code. So for each var psum possible sum in possible sums, what is the thing that I want to do? Okay, so at each step, so let's imagine here that I is like 5. Okay, so we have some elements here, like 1, 2, 3, and 4, and we want to add the 5th element. Okay, so 5, and we have to add the 6th element here. Okay, and we have some set of possible sums, and we have to extend it with the new sums. How do we get those new sums? So 6 plus every single value that we have in here, Okay, how did I call this set in my code? The possible sums to add. So what do I have to do here? For every sum that I have here, I would like to add something to my possible sums to add. What is that gonna be? Possible sums to add dot add, and someone said it like 2 seconds ago. What do I have? So how do I obtain the new sums? The element, so element of I plus p sum, right? Because elements of I was the 6 up here, and then p sum is every single element in the sum that I already have. Yeah, I guess this is a lot easier if you were to write it yourselves, because when I describe it step by step, with the pictures and so on, it sounds easy, but right now, it sounds a little bit harder. So yeah, this is the new sum that we get, okay? And after that, we would have to combine this with the possible sums that we already have, right? So we have to do we have to go through each one of these new sums that we have. So for each var no, sorry, this is a for loop. We can do it as well with for each, but this one would be easier. So from j, from I to possible sums to add dot count, right? We want to go through each one and check whether either we already have it, and if we don't, we want to do the corresponding things with this list and with our dictionary. And this is exactly what we will do. So if it's not already possible sums dict dot contains key of possible sums of j. Okay, so what does this thing say? So if this dictionary does not have the current sum, and please note that when we access this, we are going to get either true or false. So if it's false there, then this means that we don't have this value yet. Yeah? Or, what's the or gonna be? So this is if we, what happened? So this is if we do not have the current key, like if it's, no, sorry, this is if we have the current key and it says false, then we want to add it. What's the second option gonna be? Sorry, if we don't have the key. Let me check if that is fine. Contains key. Let me just write it and I will try to guess what I was doing here. Maybe I think it's that what you said. So possible dict of possible sums to add of j. Alright, so the first one is if we do not have the key, which means that we haven't added it to the dictionary. The second one says, well, if we have it, but it's false. Okay, if we added it and it's false, which happens sometimes. All right, and inside here there are two things that we have to do. What are those? Possible sums dict of possible sums to add of j equals true. Is this line clear? So in our dictionary we had sums on the left and boolean on the right. So we want to have this specific sum, which let's say is something like 35. Then we want to have this thing here, the 35th element, to be true, which means that we'll have it. And there is one more thing that we have to do. Possible sums. Right? This was the array that kept track, of all sums as well. Possible sums dot add possible sums to add of j. Can someone tell me, because it sort of seems that we use two structures that do the same kind of thing, right? We have the dictionary, which keeps whether we have true or false, depending on whether we have the sum, and we also have another list which keeps tracks, which just stores all of the sums. Can you tell me why I've chosen to get those two structures in the algorithm?
And the first one just checks if the sum is true or false, and the second one with the calculation.
So the first one checks whether the sum is in there. I could have okay. So the proposed answer is that the first one is done is used. Sorry, the second one, the possible sums. This one is used only for the calculations, and the first one is used to check. Well, that's sort of true, but not quite. Okay, so you don't need to check with another for loop inside here whether the current possible sum to add is already in our possible sums. Okay, so how would that go? Let's say that here my current sum that I want to add is like 5. How would I check this? I would go through the list, every single value, and I would have to say, well, is it here? Well, yes it is, or no it's not. Do I have to add it? Well, either yes or no. Okay, which takes how much complexity if I want to find a specific value in the list? N. It took it takes n steps, the worst case, right? Instead we use a dictionary which takes how long to find these, to do these operations, contains key, and if we have the element at all. How many? Well, yeah, it's a constant number of steps. So instead of doing n operations here, we just do like O of 1 for this specific if. Otherwise, I would have to have another for loop, which would go in and check for the list every single value. If it's in there, if it's not added, if it is, then go on. Otherwise, we will have lots of repetitions, right? Okay, and I think that's that. Okay, so now let's do a for loop to finally print the answer, which is going to be for I to possible sums console write line possible sums dot count. Sorry. And in here possible sums of I. Okay, and return possible sums dot contains, is there contains sum. Is that gonna work? I hope that it is. So otherwise I would have to do another for loop here, which is sort of fine. Alright, so let's print that and see what's going on. So set a startup and let's run this. See if it works. If it doesn't, it would be kind of sad. But I'll have to fix a bug if there is one. Yes, there is one. The given key was not present in the dictionary, which is a problem. And I think I fixed it today, but I did fix it, I'm pretty sure. So if contains key or possible sums to add of j equals true, possible sums add, possible sums to add j. Okay, I'll need to pause this, but I'm sure that I can find the bug relatively quickly. I did it today as well. So yeah, just give me a second, I guess. Okay, so the error was here contains key should have been possible sums to add clearly because we do the same check after that. It was just a typo. And now we get all possible sums here, and we get a true as well. In fact, let's not have this for loop. Let's have let me just remove that. So string.join, and in here I can have a separator, which let's say that it's a space, and we can just give possible sums, and I think that will be fine as well. Another bracket maybe, and okay, so these are all of the sums that we can get. They're not sorted, but we have true for the current sum, which we gave to be like 7. All right, so which one do we not have? Let's try with 12. Let's try with 12. That should be false. Let's try something different, like a 9. And that is true as well. So it seems that it's working. So for your homework, you would have to reconstruct how did we get the current sum, and whether you can do a sum of 0, which clearly right now is not going to work. But I'm sure that a small fix and you would be able to do it. All right, so are there any questions on this problem? No? No, it's like, again, the most important thing is start from something small that you can solve and see how you build your way up to the solution. It was the same with the labyrinths as well, right? So we can start with how much can we get here, how much can we get here, how about here? Okay, so now I'm in a step that really matters, and it's a bit different. How would I solve this? And then you get your single step. That is the important thing in those kinds of problems. The last example of this lecture will be to find the largest increasing subsequence of a set. So let's have this set, and I want to delete that as well, actually. Not this one, the other one. So let's have this set, okay? And by deleting some values in here, we would like to obtain the largest increasing subsequence. So how would you do that? So delete some numbers to get the maximum possible increasing subsequence. Can I pause? Yeah, I will pause. That's fine. All right. To be honest, maybe we should change this to the longest, which means that after deleting some numbers, we would have to end up with a subsequence which is increasing and has the most elements possible. So by deleting the 11, the 1 and the 2, we have 3, 4, 5, 6, and 8, which is increasing and is the largest. Okay, and I'll pause once again to give time to the people here to try and solve this, which is sort of similar to the previous problem, but I think it's easier as well. It's slightly different, but it would be easier to come up with a solution. So you should try that as well, and we'll get back in a second. Alright, so we managed to figure it out, and let's start the same way that we always do. Let's start with some smaller, step. Okay, so we have 3, and let's down here have the largest subsequence, which is increasing and contains this number 3. Okay, so in this case it's just 1. Okay, 1 is the largest. We have a set of 3. It's increasing, Let's add the other one. So the other one is 11. Okay, now we compare it with the 3, and we get that, well, yes, it is bigger. So and going back to the previous problem up to 3, the maximum number, the longest sequence is just 1, so I have to add 1, which is now becoming a 2. Now let's add the 4. Alright, so we know that the previous increasing subsequence was 2, but in fact we have to look through each one of these numbers. So where would we add the 4, or is it at all smaller, bigger than some of these values here? So we compare it with the 11 and we say, well, yeah, it is smaller, so we cannot make a largest one, which is of 3 elements. We compare it with the 3, which has a maximum number of increasing subsequence, which is 1, so we add the 3 and the 4 and we add a 1 to it, becomes 2. Let's do the other one, which is 5. Okay, so 5 is bigger than 4. The largest increasing subsequence up to the 4 was 2, so we think that this might be a 3. Okay, is there a bigger one? Because if this one was like a 3 and this number was smaller, we might have had a bigger number. So we have to compare the 5 with each one of these, and we see that so 5 is less than 11, so we don't care about it. 5 with the 3 would only give us a sequence of 2 elements, so in fact we have the 3 in here as well. Let's add the 1. Okay, so 1 is smaller than the 5, but it's also smaller than all other values. And in here, what is the largest subset which is increasing and has the 1? It is 1. Okay, and we keep going. We add the 6. So 6 is bigger than 1. This would be like a 2. 6 is bigger than 5. This would be like a 4. And 6 is bigger than 4. This would be like a 3. We see that the largest one before that, such that 6 is bigger than the value, is 3. We add 1 and we get a 4 in the end. We add the 2, which is only bigger than the 1. So if we had to have this 2, the largest one would be 2. And finally, we have the 8, which is bigger than like all of them except for 11. And then we have here, we have to add the 4 plus 1 is 5. I hope that that's sort of clear, because now I'm going to be doing the algorithm, which is relatively short. So new project, definitely shorter than that one. So 3, this is going to be largest increasing subsequence. Okay, so let's start. Let's have a sample array. Let me change that actually. So this is going to be largest subsequence. Yes, I want to change the class. Alright, so let's have an array. So there's going to be int sample array, which is going to be 3. Oops, what happened? Okay, this way, and I want to have 3, 11, 4, 5, 1, 6, 2, 8. This is the one that we had. Control A KD. Okay, and let's call the method, which is largest subsequence calc, and we would like to give I think just the array, so it's going to be sample array. Control dot generate method, and let's do that. Okay, so we would like to have an array like the one at the bottom, which kept track and stored all of the possible subsequences up to this value, which was also including this one. So this is the array at the bottom that I was drawing. So let's get that. Int maximal subsequence count is going to be new int array of how many elements? Sample array dot length. Okay. And what is it after that we want to do? Well, let's assume that the first one is 1. Like we can get the first element. It's increasing subsequence. So let's do that. Maximal subsequence count of 0 equals 1. Okay, and now we would like to have a for loop going through and adding each element once. But we think that we've already added the first one, or the 0th one. So let's start from the second. So it will be for I from 1 to sample array dot length. And what is it that we have to do in here? Just give me a second. Okay, we have to calculate for each new element that we have. We have to calculate all the sums plus 1 of the elements before that, but that's going to happen only if this element here is bigger than the one before. Okay, so let's keep track of all of the values that we have to check. So I was writing something like here 2, 4, 3. Those are the candidates for the biggest sum that we can get, or the largest increasing subsequence. So let's have that, and I call this var max sequence helper is a new list of int, and yeah, I guess that's that. Okay, so now we have to go through each element from the beginning and add it to this list if it qualifies. So for this is going to be j from 0 to what? To I, right? So this is the ith element, and we have to check against all values before that. So j is going to be from 0 up to I, but not inclusive. All right, and in here we have to first check if array of I, if sample array of I is bigger than sample array of j. Okay, if it's bigger than one of the previous elements, then we wanna take a look at the value and store it in this max sequence helper. So this is gonna be max sequence helper dot add. And can you help me? What should we be adding? Okay, so we have the array. Let's say that we have here 2, 1, 6, 8. Okay, and let's assume that up to here we've calculated the values 1, 1, and 2. Okay, how would I calculate this value? Okay, we go back from the first one, which is from the 0th, and say, well, if the 8 is bigger than this element, and this element, we want to put some here, or calculate the possible values, which in this case are 2, 2, and 3 by adding the 8. So which one is bigger? Which one is the biggest? It's 3. So we know that we have to put a 3 here. So what I'm asking, in this small thing here, which I'll put in green, what is it that I have to add? Maximal subsequence count of it's not I, it's j. Well, yeah, it's either the one or the other. And then plus 1. Yes, that's that. Okay, and if now we so that's it. Okay, the rest is just printing out the answer. So you see how quick this thing is. Otherwise, we would have to go once again through all possible cases, which are 2 to the power n. And this case is very, very simple. It's just you know, 2 for loops nested, which are very, very quick to execute. Okay, so here we have max sequence helper dot count. So if we manage to find some at all dot count bigger than 0, then we would like to say maximal subsequence count of I equals max sequence helper dot max. So we want to have at the ith place, we want to have the maximum value out of this helper array. So it was like that 2, 2, 3. We would like to have the 3 because it's the maximum. Okay, and else, okay, so else if we couldn't find anything which is bigger, like this, like the 1 in our previous example, which was smaller than anything else, we would still like to have a value because the next time we go through it in the array, so let's say that here we don't have a value, on the next step we might get an error. So else we have to say maximal subsequence count of I equals 1. Right? It's in its own subsequence, which is of length 1. And finally, we just need to print out the result, which is down here. Console.writeLine is going to be maximal subsequence count dot max. Okay, so we want the maximum number in this sequence, which is going to be just that. Okay. Let's have a look. Set as start a project, and what did we say? It was with 5 elements, right? So the 3, 4, 5, 6 and 8, and hopefully we should be getting a 5 if it builds fast enough. Okay, we got the 5. Let's try and make it a little bit different, I would say. I don't know, let's put a -1 here, like different but so that we can calculate it at least. So let's put a 7, a 9, maybe a -5. Okay, so what's that now? So it's again 3, 4, 5, 6, 8, and 9. Okay, so we've added just one element. It's 6, and so on. And you can test it. It's gonna work. Okay, is this one clear? It's easier and shorter. We just need one list to keep track of all of the all of the maximum sums defined by our property. But yeah, there were different ways, so you got into the right direction when we were discussing the problem. But using this method, you can now recall or print which is the largest, which is, and not just how many there are in this sequence. You can recollect what is this sequence specifically, but you have to add something to this algorithm as well. So save all, and let's finish quickly with the presentation. Oh yeah, here I had to do Control-Z a couple of times, maybe. Yeah, okay, so this is the same thing that I explained. So 1, 6, the 1 is 1, 6 is bigger than 1, so we have 2, 2 is bigger than the 1, we put 2 here. 4, we take the 2 from here because 4 is bigger than 2, so we get a 3. The 5 here is bigger than the 4, so we put 4 here, and 0 is less than everything, so it's just a 1 here that we put. Okay, homework. So implement both Labyrinth problems. Those are very, very simple. Okay, so you just need to have some array, you have to put some numbers in it, and then print the final one, which is the caret. And then here you have to do the same thing, so it's kind of the same. It's just your step is slightly different. You will be changing one line pretty much. Okay, so in the 2 problems that we last discussed, reconstruct all possible solutions. Okay, so this might be a bit harder, but I've already given you, half of the algorithm, and you have to add something to make it work. Okay, in number 2, you should also, yes, you should also reconstruct solutions, which I'll put in here, reconstruct solutions, which is going to be very, very easy for the first problems. Okay, so this is number 2 and 3, where you have to do that. And 4, attempt to solve the shortest path problem in a graph with dynamic programming. You can look at the picture on the first slide. Okay, and that's what we'll do now, and then we finish the lecture. So what do I mean? So this is again with some graphs, and DP problems, DP solutions are very common in graph theory as well. And let's try and solve this one. So what's the shortest path from A to Z? Okay, and we have to solve this with dynamic programming. I'll give you a couple of minutes to think about it, but it's easier than the last couple of problems that we did. So you just have to think on this one. I'll show you the solution in a second, and then you have to implement that for homework when you get back. Okay, so let me pause. Alright, so the shortest path from A to Z. This can be done with a recursion, which just takes all possible paths and so on. You want to have the path to Z, and you can do it by going back this way or this way, and just work your way around until you reach the A, and you can check all of those, and then you can pick the one that is the smallest. But there is a clever way to do that. So let's start with the A first. Okay, so A is our starting point, so we don't care about that. Let's start with all of the neighbors, and here I'm giving you a hint by the way I'm talking about the homework. So look at all of the neighbors of A. Okay, so those are B and H. And how many ways can you get to B? Well, that's just one way, so that is 5. Okay, so 5 is the shortest path from A to B. And with this algorithm, we'll calculate not only the shortest one to Z, but the shortest one from A to any other vertex in the graph. Okay, so from A to H is 3. Okay, take a look at D now, which is a number of both H and B. Okay, so you can get into D by H and B. So from B, the shortest path before that was 5. So 5 plus 1 would give us a 6. And then we have the 3 plus 5, which would give us an 8. The shorter one is 6, so we put a 6 in here. Let's now have a look at C, which has, so the in edges are from B, from H, and from D. So let's calculate which is the smallest. Okay, so 5 plus 2 is going to give me a 7, 3 plus 2 is going to give me a 5, and 6 plus 1 is going to give me a 7. So in this case we have 3 plus 2, which is 5. Okay, so this is the shortest to C. Okay, so which is the one that we should pick next? Okay, we have the F. There are 2 ways to go to F. So one of them is from C, the other one is from D. From C we have 5 plus 3, which is 8. From D we have 6 plus 1, which is 7. So here we put a 7. Okay, and finally to E, before the problem is kind of clear. So to E we can go from C, from D, and from F. So let's try all those. So this is going to give me 12. 6 plus 2 is going to give me 8. And 7 plus 2 is going to give me a 9. So the shortest one here is the 8. And then we have 2Z, we either have a 12 or a 9. It's clearly the 9. Okay, and finally the path is So how do we reconstruct it? AH, no, sorry.
Yeah, that's worse.
No, ABD,
E,
EZ.
there's another one.
There is another one. Which is that?
A, H, C, D.
AHCD. Where is that D?
You can go from the
Okay, yeah, you can't go from there. So yeah, it's just one, and the answer was this way, this way, this way, and this way. Okay. So how can you come up with this? Well, let's say that we are at C. So how can you? So you know, it's clear when you start with the smallest one, but we need to have the step, right? So let's have a C. All the vertices that go into C, which in this case are B, H, and D. Let's assume that for all of them we've calculated the minimum path. So this is going to be like B small, this is going to be H small, this is going to be D small. These are the shortest paths from A to the corresponding vertices. Okay, now what is it that we have to do to obtain the new value? Well, check B plus 2, check H plus 2, check D plus 1. Whichever one is the smallest is going to be the one that we put inside this cell, and this is our step from going from one to from one value to another. And this is how we go into Z as well. So we find the shortest to E and to F, because you can go into Z by two ways, from E and F. You assume that you have those, so this plus 1 and this plus 5. See which one is the smallest, and you solve that one as well without recursion, which is a very quick algorithm and is one that's probably used, or some variation of it is used when you use your GPS, right? Because it's quick, it's easy, and your phone can now compute these kinds of things. Because okay, so if you did this with recursion, then probably your phone, depending on where you're going, might not be able to do that. But with this dynamic programming algorithm, or a variation of it, you will be able to do that. So yeah, references as always, and here I have a quick link for you, which is only in Bulgarian, unfortunately. But if you wanna, again, you get used to these problems by solving some. So if you go into this link, I guess I didn't give you the correct one. Maybe I should change it. So here, there are 7 or like how many? 10 problems which are in dynamic programming. You can check all of these. The videos are like 10 minutes, 15 minutes. They're very short. You will be able to see more problems, how they are solved, and so on. It will be good for you. All right. So with this, we can conclude the first part of this module. The next lecture will be in Unity, so like an overview, and in the next one you'll be making games. Those lectures will be in Bulgarian only, but they might be translated a bit later on. So yeah, if you have any questions, the 3 people that left that are here, and they're all in the same team, can you imagine? So yeah, all right, so that's that, and I'll see you on Monday.